We are going to, oh, this is way louder. But it worked, so, whatever works. I need you to be super, super quiet because I have an announcement to make. Hi, my name is Andrew, and I've been doing a great job at capturing this conference in written word. I am absolutely awesome. Please give me a round of applause. Nice. All right, we have 2 talks coming up, then there's a break, and then we have 1 more talk coming up, and then there's going to be the closing notes by Ramon and Pilar again, and then there's the after party, of course, at 8 tonight. So our next speaker is Brad. I've heard that he is quite the karaoke singer, and a barbecue enthusiast, and a coder, who would expect that. And he has about 15 years of experience with SQL under his belt. So, if you're about to embark on your next, designing your next database challenge, he is probably the best to help you with that. So, Brett.
Could also talk really loudly. Hi, how are you doing? Guten Tag. Did I say that right? Okay. I'm very happy to be here in Vienna. This is my second time. I was here in 2003, and I could not be more thrilled. I flew out here from Los Angeles last night just to speak to you all, and this has just been a lovely time. Thank you all to our organizers and all the people who set up this conference and invited me up here. My name is Brad Urani. I am a staff engineer at Procore in Santa Barbara, California. And this is a talk about database patterns, Rails anti-patterns or relational anti-patterns. I changed the title depending on who my audience is, but it's the same talk. Rails anti-patterns, how not to design your database. Warning, tough decisions ahead. I'm going to give you some patterns you can use in your database, but realize at the end of this that I cannot give you hard and fast rules over exactly what to use where. I'm going to hopefully give you tools that you can add to your tool belt, new things to try, but ultimately, at the end of the day, making decisions about design patterns is difficult and it's very specific to your use case. At the end of this, realize that there are still choices to be made. I work for Procore. Procore makes software for the construction industry. We make software for people who build skyscrapers, giant buildings like this. This is an example of one of our iPad apps. It's a blueprint management app for construction plans. Here's a gentleman out in the field using it, and it is a man. Construction has a similar problem to software in that most of the people are males. But we do have some programs in place for increasing gender diversity in the construction industry, and we actually modeled them after a lot of the Rails programs for this, things like Rails Girls and things like that. We're pretty proud of those. We're also big supporters of the Ruby community. We sponsored RailsConf. We were the diamond sponsors of RailsConf the last 2 years. And we, thank you, I appreciate that. We do Postgres database, a SQL, at a very, very large scale. 60 million rows scanned a second on our primary database instance is, that's pretty big. Even, I gave this talk at PostgresConf in Jersey City, and even the Postgres people were somewhat impressed at that. 50,000 transaction seconds is probably even a more impressive number. That's reads and writes. There's an implicit transaction in every Postgres read with a 14 terabyte database. And what that means is that we have to do SQL very, very well, which means we have to design our database very, very well because mistakes in the area of database design can really cost us when you're running at this scale. This, for instance, actually, this is our old instance. We have a bigger one now that probably costs as much as a new Ferrari. We cannot abuse this database, and everything we do is very database heavy. So this is an example from Procore. It's a construction budget, and when you load a page like this, it's going to run possibly 20 to 30 SQL queries just to render this page. And that is very highly tuned, very intentional SQL queries. And to get that fast, to get this page load quickly, that requires tuning this carefully, choosing the right patterns, making sure that the performance is spot on, but also there are developer happiness issues with this. We have a very large team of Rails developers, dozens of Rails developers, and one of the largest Ruby on Rails apps in the world. It is over 1 million lines of Ruby, close to 2 million lines of Ruby right now. And what that means is not only is this a SQL problem, it's a Ruby on Rails problem, which means the database patterns that we use have to work with our tooling. In our case, our tooling is Ruby on Rails and Active Record. So not only do we have to pick the right patterns that work really well with SQL queries that are performant and fast, it has to be very easy for our developers, all of our web developers, to use them. It has to fit naturally into their tool set, work with their core competencies, which is Active Record and Rails. I don't know what that is. So let's talk about anti-patterns. This talk today, I'm going to talk to you about two major anti-patterns. The anti-patterns are naive trees and polymorphic relationships. But first, a little disclaimer. There are no actual anti-patterns. An anti-pattern is only an anti-pattern if you use it in the place where it's not the best choice. If you use it in the place where it's the wrong choice. Every pattern does have a case where it is the best pattern, so even my anti-patterns that I'm going to talk to you about today can be the best choice if it fits your use case well. But trees are pretty tough to work with in databases in a lot of cases. So what's a tree? Let me give you an example. If you have to represent a file system, like maybe you've got some document management solution, then you might have a tree in your database. So here's an example of a file system hierarchy, right? An org chart is a tree. So if you have something like this, if you're representing any kind of structure like this, it's a tree. A comment thread, like something on Hacker News, is a tree, and you get all this idiot stuff. It's the same time every time on Hacker News. Someone mentions Rails, and then there are all these JavaScript fanboys. Someone says something about self-driving cars, blockchains, and all the same typical stories. Occasionally, you do get some sense if you filter throughout the noise, but regardless, a comment thread is a tree, and our anti-pattern here is naive trees. So the simplest way to represent a tree in a database is with something like this. I've got a primary key ID, I've got a foreign key manager ID. In this case, if say you're an employee at a company, you have a manager ID, which is your supervisor, your manager, and very simply with 2 columns, we have a tree right here. This is very efficient, it uses very little space. It's the easiest way to represent a tree, but it is the hardest to query. So let's take an example of something you might want to do if you have this structure. You might want to get what we have is, we might want to get descendants. So here we have Paulie Walnuts. This is from the Sopranos TV show. And he has his many descendants. Getting this out of that naive tree requires some pretty hairy SQL. So how do we get this? Well, we could start at the top, right? And we could start to join. So if you've got one person, you can do a join and get all of their direct children. Then you can do another join to get their grandchildren, and another join to get those people's children, right? The problem very quickly becomes that when you start this off, you don't know how many joins you have to do. In this case, you have to do a join for every level of the tree, but when you start this query, you don't know how deep you need to go. So this starts to break down, and it turns out not to work very well when you're trying to get descendants out of your database. Well, what else we could do? Ooh, I've got an idea. We could start at the top, and we could get the person at the top, and we could get their children with another query, and get their children with another query, and get their children with another query. This also starts to break down. This is a pattern called n+1 queries, and it's typically a bad thing to do. This is not very fast. With deep trees, you end up doing way too many queries, and you bog down your database and hog database connections, so I don't recommend this. All right, so how else can we get descendants out of our database? Ooh, I know. We could use recursion. I tried to find like the scariest tree I could find. It's like the monster tree. We could use recursion to try to find this. Recursive SQL, has anyone here tried to write recursive SQL? It kind of sucks, right? It's not very readable. It is not supported well in our ORMs, particularly Active Record and things like that. It's very hard to performance tune. And if you have a lot of developers that have to deal with database tables that you have that are trees, asking everyone in your organization to all write recursive SQL when they interface with this particular table is pretty much too much to ask. What we need is something simpler, a better way to do this. A pattern that gives people fewer foot guns, right? Here's an example of some recursive SQL. True fact, recursive SQL is not actually recursive. It's actually iterative unions. But regardless, it's not the best way to run this app. Another typical problem we run when we have trees is we try to get people's ancestors. So if we start at the bottom and we have Alfie and we want to try to find his manager and his manager and his manager and go up to the top, we also get the same problem here. So also realize that we have issues here with the end result. So say at the end of the day I want to put the results of these queries on a web page, right? The web page might look like this, nested bulleted lists. This is not how the data is shaped when it comes back from SQL. When it comes back from SQL, it is in a table. So oftentimes if we're writing recursive SQL and things like that, not only do we have to write recursive SQL, we have to write some recursion that takes the results and renders them into the tree so that we can display it. Not ideal, right? That's a waste of time. And we haven't even mentioned everything that can go wrong here. What about deleting in a tree? If you have a tree and you take a node out of the middle, you have to reparent everything, which gets very complex. Try writing those queries. Has anyone ever tried to paginate a tree? That gets pretty tricky, right? Counting, updating, insert. It quickly breaks down and gets very, very complex when you try to deal with these things if you don't find better patterns. Here's an example of a giant recursive query. This is a tree copy that I wrote. It features, among other things, cycle detection. So if you have A and A has a parent B and B has a parent C and C has a parent A, you can infinitely loop your SQL, which is not good. So sometimes you're forced to put cycle detection in your queries if you deal with things like that. Okay, but like I said, anti-patterns are not always anti-patterns. Even anti-patterns sometimes have a good use case. So if what you're doing is relatively simple, right, this might work for you, if your tree, if you're not doing a whole lot with it, it could be good. It does have referential integrity, meaning you can put foreign key constraints between children and parents and enforce integrity that way. It is very efficient on disk space. If you don't need descendants, if you don't need ancestors, or maybe you can write some recursive SQL but then cache the results, you might be able to get away with this. It might work for you. But if you're doing anything more complex, there's probably a better way. So number one, alternatives to naive tree is the closure tree. So a closure tree works like this. In our organization here, we have this is our file system example. What we do is we create a table that has a reference from every parent to all of its descendants, its children, its grandchildren, its great-grandchildren. And itself. Every node also have a reference to itself. So it looks like this. We start with this, which is just, we have a primary key ID, we have a parent ID, and in this case a name, but we've seen this before, right? We recognize this. This is naive tree, isn't it? So in addition to this, what we add on is a table that looks like this. And so here in this table on the side, what we have is a primary key and a row representing every one of its descendants, its children, grandchildren, great-grandchildren. So ancestor ID 1 in my example is Tony Soprano, and we see not only his direct reports, right, but also their direct reports, their direct reports, their direct reports. So there's a row in this table for every relationship in our tree, which is why I mentioned conceptually this is what it looks like. Not only do we have from the top file, right, we've got a row for from the root to photos, from the root to France 2017, from the root to RailsConf, and each one also has a reference to itself, which is important. So then it becomes very simple. If we want to do something like descendants, we can do that entire thing with a single join and a single where. This now is a very efficient, fast query. Very fast, especially if we put the indexes in the right place, in this case, ancestor ID, which you have to. We've drastically simplified the SQL. We don't have to worry too much about query tuning. It's a lot easier for our developers to handle, especially on larger teams. So, and we get very good performance out of these. A single select for ancestors, a single select for descendants, siblings, and various other things I haven't talked about, all come very quickly. And there's a Ruby gem for this, too, wouldn't you know it? It's called Closure Tree. We use this in production. It's really wonderful. It implements this pattern for you. It's got a lot of features, like it helps you write the migrations. It comes along, you add it to your active record models like this, and it gives you all these wonderful methods that generate all this SQL for you and save you from having to write a lot of these things. It gives you some really kind of neat advanced ones like this, where you can create like whole legs of your tree in one single query. Mutations are also pretty quick to inserts. Reparenting is the tough one. That's when you delete a node in the middle of the tree and you have to update the parent IDs of everything else. It's transactional. It does the right things for you there. And it's fast. It's referential integrity, which is something I'm going to talk a lot about today. It allows you to put foreign key constraints on your references. Deterministic ordering supports all your databases, includes migration tooling. It's pretty nice. Well, I'm not going to get into PG Bouncer, but there's another alternative. there's also Materialized Path, and this is another way to represent trees that does a similar job as closure tree, but is slightly different. So consider our file system example again. We have a primary key ID, and then we've got this path column. So here's the fun part. Path is a string, a text, or a varchar. And as you can see, it has a /delimited sort of format here, referencing every single entity's entire hierarchy in this tree. Now that seems a little weird, right? Like we're seriously representing our hierarchy as a string? Sounds a little bit odd, doesn't it? And the first time I saw this, I was like, are you kidding me? That does not sound right. There's got to be a better way to design this. Turns out it works actually really well. Believe it or not, Microsoft SQL Server uses this under the hood for its tree data type. All of a sudden, descendants becomes quite easy. We've got one little query with a single where clause, and now we've gotten descendants very, very, very fast. Now, we all know that when you do database performance, the way you make it fast is with the index, right? So pop quiz. If I have an index on path, can it use it for a query like this? The answer is yes, only if the wildcard is at the end. You cannot put the wildcard at the beginning or in the middle, but if the wildcard matches at the end, it will use the index to do this lookup, and that's the reason this is possible. That's what makes this fast. There's also a gem for this, wouldn't you know it? It's called Ancestry. It's very well maintained. I think they're looking for a new maintainer, but last time I checked, it was very up to date, and it gives you a lot of the same things. You know, parent methods, ancestors, descendants, migration tooling, all those kind of things. It's got some limits because it's a varchar 255. You can only go 23 levels deep. That could be an issue for you. There is a pretty big limitation in this approach, which is no referential integrity. That means because we're representing the parents as a string, you cannot put a foreign key constraint on that column. So there's a potential for data mistakes, right, due to programmer error, race conditions, things like that. But this is fast. So a little performance comparison. This is from a blog post by Reynard Hillman. A little blog post shows that Ancestry is typically 3 times faster than Closure Tree for most of the kind of things you would want to do in this. But in certain cases, Closure Tree is orders of magnitude faster. So which one is faster depends kind of on what you're doing, you know. Are you paginating? Are you deleting? Are you counting? If you're really concerned about performance, if your database load is highly dependent on querying trees, then you have to tailor the performance characteristics to your workload. Insert heavy workloads are going to be very different from read heavy workloads and things like that. So if it matters, if performance is the top thing, and I'm not saying it should be, if performance is top of your mind, you do have to choose these based on the specific workload that you're using. Usually you focus on reads. Typically data is written once and read hundreds or even thousands of times more than it is written, so usually you care a lot more about the reads than the writes, but your workload may vary. Beware of naive benchmarks. It's always specific to your use case. Whew. Okay, so that covers trees. How much time do I have? Where am I? Sorry. Cool. Okay, so that brings us on to anti-pattern number 2. Polymorphic relationships. Who knows what this is? Have you ever heard of this? You are all Ruby Rails developers. I say this because I wrote SQL-backed web apps for 10 years, and I had never heard of this pattern until the first time I ever used Ruby on Rails. And the first time I looked at it, I was like, what the beep is that? Like, what are people doing? Oh my God, you've got a foreign key referencing mini tables. This is wrong, dead wrong, dead wrong. Turns out I was wrong. It is actually really useful, but only for a few specific use cases. And I call it an anti-pattern because a lot of the time I see it employed or used, it's for the wrong reasons. It's a lot of times employed for the use cases which is not best for. But to be fair, I am going to talk about where it does fit well and where it is good also. So, for those of you who aren't familiar with this, this is what it looks like. This is actually the example that we ran into in a production case, which is here we've got 3 tables: purchase orders, sales orders, and receipts. They all have something in common in our sort of business design here. They all have this thing called a line item, which represents one of those lines on the page, you know. And so in this particular case, we rolled up line item into a single table. We have a polymorphic relationship. That means we've got that column holder ID. That is a foreign key to any one of the IDs in one of the parents over there. And we've got a holder type. A holder type is a string, which would be either purchase orders, sales orders, or receipts. And in that way, the holder ID foreign key is a foreign key to any one of those other 3 tables, and we know which one based on the string in holder type. Okay. It looks like this when you actually look at the data. You can see that holder ID there is the foreign key, but we only know which table it belongs to because of the holder type over there. Problems with this. Okay, well, let's talk about the good sides. It's built into Rails. Honestly, just the fact that it's built into Rails means it may be the best choice for you. It's easy. You don't have to think too much. You can just use it, and no one will fault you if you just use this based on its ease, just because it's easy and built into Rails. That's perfectly acceptable if that's what's most important to you. And it's also easy to add more parents. If I have something like, in this case, line item, and I was going to add a bunch of new parent types, it's very easy to add those. You add the new table, but you don't have to actually change the line items table. You just write new values to it. The line items table stays the same no matter how many parents you add, which, if that's what's important to you, could be very useful for you. Disadvantages is, once again, no foreign keys. And this becomes really, really important when you deal with people's data. If you are holding financial data or medical data or things where you absolutely cannot get it wrong and you have the responsibility to your customers and the people to whom this data belongs to get it absolutely right, then not having foreign keys opens you up for a lot of problems. So right there is a very good reason not to use that if that is what's critical to your app and your customers. We lose our cascading delete when you do this. It gets ugly if you have to switch to raw SQL, like doing joins off two different columns gets kind of ugly. It's not very space efficient if you've got that extra string type holder right on every row, wastes a lot of space. That's probably not a big deal in most cases, but it could be depending on what you're doing. So this comes with disadvantages. So what are some of the alternatives? Well, you could just keep it separate tables, right? In this case, probably the best choice would have just been to have separate purchase order line items, sales order line items, and receipt line items, and it would have solved all these problems. We should have just done this from the very beginning. The error here was that we had the temptation to make it dry. We saw, all these parents have these line item things. Let's make it into one table and dry it up, and that turned out to be an error. But this only works because there's never a time where I need to show data from the 3 child tables all on the same page. These are separate pages. We never need to combine all that stuff. In a lot of cases, you do. So this one works in a limited amount of cases, but not all cases. Let's look at another example. So the lesson there is it's okay not to be dry. Okay, so another alternative here, right, is exclusive arcs. This is another way to represent the same data. And I'm going to use a slightly different example here. This is sort of like the social media, like the Facebook example. So say you're running a social media site. You've got photos, and people can comment on a photo. You've got posts, and people can comment on a post. You've got invitations, and people can comment on invitations. So in exclusive arcs, what you'll notice is we have photo ID, post ID, and invitation ID. So we have 3 foreign keys because we have 3 parent tables. Okay, it looks like this when we look at the table. You have 3 foreign keys, and in each case, you have 1 that's filled in and 2 that are null. So, advantages here, right? You can have your foreign key constraints. Now you can use the database's powers that it gives you to make sure that this data is correct. Mistakes, right? There are possible mistakes. That is, you could have a bug in your code that fills in 2 foreign keys, but more than 2 foreign keys in one row. 1 or more foreign keys in the same row. You can put constraints on most databases that protect you from that. One of the downsides to this is you might have mini indexes. So for instance, to make this fast, you have to put a foreign key on all of your, or you have to put an index on all of your foreign keys. Too many indexes will slow down your queries. They speed up reads, but they slow down inserts and updates. So if you have a lot of different parent types, you have a lot of indexes, and that could become a performance bottleneck. All right, so another alternative is this pattern called base parent table, and it looks like this. So first of all, on our parent table, what you see is you've got a commentable ID on this side. So we've moved the foreign keys over to the right side, and then we have a table in the middle called commentable, the ID of which, the primary key of which references the keys on that side, and then we've got comments over here. Now, look closely at this. You'll see that we have a messages on commentables and a message on comments. The message on commentables is the message that goes along with the photo, post, or invitation. What we've done here is realize that all 3 of these things on the right side here all need messages, so we can move it to the table in the center. The actual comment also has a message, which is what lives over there. So what we've done is sort of like the database equivalent of inheritance, is we've extracted the common fields and put them on the commentable table in the middle, which can save you if, for instance, in certain pages, you might only need to render the things from commentable. You might not even need to query the data that's on this side. Maybe, depending on what you're doing. Advantages to this, so by the way, that is 1-to-1. So for each commentable, we have 1 photo, or for each photo, we have 1 commentable. And it's 1-to-many over here because they can all have many comments. Advantages, it is dry. In this case, that's a good kind of dry. Disadvantages, we now have 2 joins. Now, databases are designed to do joins. They are very, very fast at joins. So probably if you've got the right indexes, that might not be a bottleneck, but it might. You have to be careful. One of the drawbacks we do find in this as well, it's very easy to go from this way, from the right to the left. It is very hard to go the opposite way, left to right. So depending on which way you're joining, that might be a limitation. Errors are still possible. Does anyone see it? How you can mess this up? Well, you could have the same commentable ID appear in more than one of these tables on the right, but that'd be a pretty strange bug. It's not likely, so this is in most ways safer. So, just to recap here, if you have, right, because now we have to actually make choices. We have these decisions to make. We have a few more patterns in our tool belt. If you have dozens of possible parent types, so this is a case that we have at Procore. So we have a change tracking table. So what that means is that we have dozens of tables, and every time one of those is changed, we want to make an entry in the change table. That means dozens of possible parent types. Actually, in our case, it's hundreds, and growing every day. How do we make that relationship? What is the best choice in this case? Any guesses? Polymorphic relationships. That is where this really, really shines, when you have a large and growing number of parent types. It's simple and mostly safe. It's built into Rails. Sorry. What if that doesn't work for us? What if we want our referential integrity? We want our foreign key constraints, and we have relatively few parents. Exclusive arcs works really well. That's the one where you have a foreign key for each of the different parent types. If we've got a lot of shared fields, if we've got a lot of functionality we want to encapsulate that's common to our parent tables, and then we want good foreign key constraints, base parent table works really well. That's like the commentable example. As always, these things, your mileage may vary. There are a lot of trade-offs here between performance and simplicity. In some cases, performance is everything. In some cases, developer ergonomics and the developer experience is a lot more important. There's a case of correctness, in this case, like having your referential integrity, being able to enforce your business rules with database indexes, unique constraints, foreign key constraints. Comes at the cost of convenience, which is things like polymorphic relationships that are built right into your Rails framework, which make it really, really easy to use. You have choices at the end of the day, and you can only pick the choice that fits your use case the best. So make good choices. Realize that the pattern that's most obvious to you might not be your best one, whether it's trees or these other types of relationships, that there are more than one good way to do things, and it depends on what you're doing. Congratulations, you avoided recursive SQL hell. There are a few books that I recommend for these things. Trees and Hierarchies in SQL for Smarties. This is a riveting page turner. It will keep you up all night long. I'm just kidding. It's like really dry and hard to get through. This other one, no disrespect to the author, but it is really good and complete. This one is more readable. This one you can actually read cover to cover. I enjoyed it. And it details these types of anti-patterns and more. Bill Carwin is very excellent. I'm Brad Urani. Follow me on Twitter. I'm a total addict. Reach out to me at LinkedIn. I work in Santa Barbara at Procore, beautiful Southern California, full of home to perfect weather and wildfires at the moment. Oh my God, pray for us. This is the view from the office. We are hiring all kinds of roles: Ruby, Android, iOS, security, DevOps, machine learning, all of it. So come move to California, work with me. We've got seals, sunshine, and sharks.
Super scary. Slow motion walking. Oh, another round of applause for Andrew, because that was so quick. It was difficult to follow along. Also, even more. To write it all down. I love when I get a question, where is the laptop? That really, calms my nerves. I think, Brad walked away with a laptop. I'm not sure if that's the laptop that you're... We have a case of a missing laptop. Yeah. That was exciting, sort of Sherlocky. All right. After this talk, we have a small break, and then I want you all back at 4:30. Yes, for the last talk of today. And then after that, there's a tiny break, and then there's the closing notes, as I have already said. The next speaker is Coraline. She is a writer, a very well-known speaker.